if we increase or decrease the temperature in case of gases are dissolved, gas is dissolved in liquid, then what will happen? So in this case, it is normally opposite of what you see if you dissolve, say, sugar in water. If you increase the temperature, in that case, the solubility increases. But here in this case, it is opposite of that. Solubility of gases in liquids decreases with rise in temperature. So if you increase the temperature, gas comes out of the liquid. So that's why solubility decreases. The gas which is present in the liquid part, so say gaseous molecules are there. If we increase its temperature, if we heat it, these gaseous molecules, so say oxygen dissolved in water, okay, that will come out. This oxygen will come out of the water, and it means the solubility decreases with increase in the temperature. And this is one of the reasons why aquatic animals prefer the cold water instead of hot water, because in cold water more oxygen is dissolved. So aquatic animals feel comfortable in cold water instead of warm water. And the reason, if it is asked, as dissolution of gases is an exothermic process. So dissolution of gases means when gas is dissolved in liquid. So say carbon dioxide is being dissolved in water and we are getting a solution of carbon dioxide as solute and water as solvent. This process is exothermic, means heat is evolved. So if we increase the heat, as per Le Chatelier's principle, if we increase the heat, it will go in backward direction to reduce the heat. If it goes into backward direction, means carbon dioxide and water will get separated. Carbon dioxide will get out of the water, means solubility will decrease. So the reason solubility of gas decreases in liquid on increasing the temperature is that this process is exothermic process. The dissolution is exothermic process. Hence, on increasing the temperature, the reaction goes in backward direction and the solubility decreases. The question is, if the solubility of H2S in water at STP is 0.195 m, calculate Henry's law constant. Okay. So it gives you a lot of information. 0.195 m gives you information. What you need to calculate the Henry's law constant, Kh. And you know the relationship. Okay. And you know the pressure because it is given STP. And you can calculate the mole fraction because the molality is given. So how you proceed? You will say at given conditions, the molality is 0.195. It means 0.195 moles of H2S are dissolved in 1000 grams of water. What is definition of molality? Molality is, small m means molality. It is number of moles of solute in 1 kilogram of solvent. That is number of moles of solute divided by mass of solvent in kg. You know that. That's why it is number of moles of solute in 1000 grams of solvent, which is water here. So we know this thing. This gives us the information. This gives us the information that we have 0.195 moles of H2S dissolved in 1000 grams of water. And we can calculate the moles of water from here. Moles of water will be given mass upon molar mass, that is 55.55 or 55.56 moles, and H2S 0.195. So you can calculate the mole fraction also. So from here, you got the number of moles of water, and with number of moles of H2S and number of moles of water, you got the mole fraction of H2S as number of moles of H2S divided by total number of moles. Substitute the values. You get the mole fraction of H2S. Okay. In examination, if you want to save time, you can write it like number of moles of H2S equals to number of moles of H2S divided by number of moles of H2S plus number of moles of water. This is acceptable. This is formula. Okay, generic formula, universal formula you can use. So substituted the values, you got the mole fraction of H2S. Mole fraction of water, you can get 1 minus this one. Okay, but I think that is not required because you are asked to calculate the Henry's law. Okay, so Henry's law will be P equals to KH x. You calculated the amount of solute dissolved in water in terms of mole fraction. At STP, pressure is 1 atm or 0.987 bar. You can take 1 atm also, okay? In that case, the unit of KH will be atm. That will be the only difference. So here you know that at STP, the pressure is 1 atm, or in bar, if you convert 1 atm to bar, it is 0.987 bar. Substitute the values. KH equals to P by X. You get 282 bar. That is the answer. Now see the question only and try to find out whether you will be able to do it yourself or not. Try to recall all the steps. Start with the molality 0.195 m, means 0.195 moles in 1000 grams of water. 1000 grams of water, 55.56 moles. So you got moles of both, you got mole fraction of the solute, okay, that is gas in water. The moment you got mole fraction, pressure you know at STP, you get the Henry's law constant by using the relationship P equals to KHX. Yes, in ATM Ashi, it will be 285.7, correct. Okay. Correct. Next question. Henry's law constant for carbon dioxide in water is given. And it is given in terms of Pascal, means pressure is being taken in Pascal. Calculate the quantity of CO2 in 500 milliliter of soda water when packed under 2.5 atm CO2 pressure at 298 K. Temperature is same. Read the question carefully and then I'll explain. First, write what is given and what is asked. Then you will be able to find the relationship yourself. Okay. Carbon dioxide dissolved in water is known as soda water. Soda water is nothing but carbon dioxide dissolved in water. Okay. So the pressure at which carbon dioxide is kept, there the solution is kept, is 1.67 into 10 to the power 8 Pascal. That is actually the Henry's law constant. KH is given. You are asked calculate the quantity of carbon dioxide in 500 milliliters. So if we take 500 milliliter of this water and pressure is 2.5 atm, then calculate the quantity of carbon dioxide. So if you have gone through the question, try to understand, then I'll explain. If you don't understand the question, you will not be able to get the answer. Okay. One now, okay, I'll explain it. Okay. So remember, KH is given in Pascal. Pressure is given in ATM. Okay. So KH is given in Pascal. You need to convert the pressure also in Pascal. So only one unit. Either you convert Pascal to ATM or ATM to Pascal. So here the partial pressure of carbon dioxide 2.5 atm, we need to convert it to Pascal, and when we convert atm to Pascal, it is 1.01 into 10 to the power 5. That is acceptable. Instead of writing 1.01325, okay, this is used. So this is exact value, but 1.01 into 10 power 5 is acceptable. 1 atm is equal to 1.01 into 10 to the power 5 Pascal. Now we have same unit. We move forward according to Henry's law. The partial pressure will be equal to KH into X. So from here, we get X 0.00152. This X is actually the mole fraction of carbon dioxide in water. Mole fraction of carbon dioxide in water. Mole fraction of gas in the liquid. Okay. So I'm going back just to show you the question what is asked. Question asks about the quantity of CO2 in 500 milliliter. You got the mole fraction. You got the mole fraction. From this mole fraction, how to get the quantity? For that, write the formula of mole fraction so that you can get moles of carbon dioxide, because you have to get mass. Mass you can get from moles. Moles you will get from mole fraction. Always write in this fashion if you are confused. What is required mass? For that you will need moles of carbon dioxide. Moles of carbon dioxide can be obtained from mole fraction, which can be obtained from Henry's law. So Henry's law gave you mole fraction. Mole fraction will give you moles of carbon dioxide. Moles of carbon dioxide will give you mass of carbon dioxide in 500 ml. Here we have done approximation that the number of moles of carbon dioxide dissolved in water, so as compared to water, it is the amount is very, very low. Okay. How do we get this? That amount is very low. Okay. So just here. Okay. The Henry's law constant is 1.67 into 10 power 8 Pascal, means this amount X, okay, if you see is 0.00152, means XH2O will be 1 minus 0.00152, that is 0.998 something. So as compared to the mole fraction of water, the mole fraction of carbon dioxide is negligible. This is actually XCO2. It is negligible. As compared to water. So that's why here in the denominator, as compared to water, we have neglected CO2. Not in the numerator, because in numerator it is not being compared with anything. Okay, we can neglect only if it is an addition or subtraction with anything. So in 500 milliliter of soda water, the volume of water will be approximately 500 milliliter. The density will be approximately the density of water, because carbon dioxide dissolved is negligible. So the volume of water will be 500 ml total. So 500 ml water is equal to 500 grams of water because density is 1 gram. And that will give me the number of moles of water. Number of moles of carbon I have to calculate. X I know. I have calculated X here. This I know. Number of moles of water I have calculated. Number of moles of carbon dioxide will be obtained. Substitute here. Okay. Substitute here and you get the number of moles of carbon dioxide. The moment you got the number of moles, you can convert it to mass by multiplying it by molar mass of carbon dioxide. So understand the path and then you will be able to solve these questions. You need mass of carbon dioxide. This is something you can get from moles of carbon dioxide. Moles of carbon dioxide, you can get mole fraction of carbon dioxide. Okay, basically both mole fractions will be required. And mole fraction you got from Henry's law. From Henry's law, you got mole fractions. From mole fraction, you got moles. From moles, you got mass. Next topic, vapor pressure of liquid solution. Another very important law here. We have talked about Henry's law. Okay, that is the amount of or the mole fraction of the gas dissolved in the liquid is proportional to the partial pressure above the liquid. Here we have Raoult's law. And remember what we are talking about. We are talking about liquid solutions. Two liquids are mixed. Two liquids are mixed. For that, there is Raoult's law. Raoult said that for a solution of volatile liquids, means say liquid of mixture of alcohol and water, both are volatile. Alcohol is volatile and water is also volatile. So for a solution of volatile liquids, the partial vapor pressure of each component of the solution is directly proportional to its mole fraction present in solution. So basically, Raoult modified the Henry's law. Okay, one step ahead. So instead of just one liquid and gas above it, Raoult's law is talking about two liquids mixed together and both are volatile. So both will have their vapors above them. In a closed container, they will cause the partial vapor pressure. And due to that vapor pressure, some amount will actually be vaporized. Okay, always vaporized. So this law says that the partial vapor pressure due to vaporization is directly proportional to its mole fraction present in the solution. Mole fraction present in the solution. And remember how it is different from Henry's law. Henry said the partial pressure of the gas in vapor phase. Okay. In Raoult's law also we are talking about partial pressure in vapor phase is proportional to the mole fraction of gas in solution. Mole fraction of gas in solution. Here also we are talking similar things. Similar thing. The partial pressure of each component now in this case directly proportional to its mole fraction again present in the solution. So the way we write it is for one component, the partial pressure is proportional to its own component. So we will write it P1 equals to P1 naught. So remember here we are not writing KH. Here we are writing P1 naught, where P1 naught is the vapor pressure of the pure component 1 at the same temperature. Pure component 1 at the same temperature. Similarly for component 2, P2 equals to P2 naught X2, where P2 naught is a constant in this particular relationship, and it is the vapor pressure of pure component 2. Pure component 2. Means other component is not present. Pure component 1 means 2 is not present. Pure component 2 means 1 is not present. Then, so for that, we know P1 naught, P2 naught. These values are normally constant. Okay. The vapor pressure at a particular temperature of a particular component is constant. But when we mix these, then these will be different, and we can get those partial pressures by this relationship. P1 equals to P1 naught X1, P2 equals to P2 naught X2, where X1, the mole fraction of component 1 in the solution, X2, mole fraction of component 2 in the solution. So it is very similar to Henry's law, but for two components instead of one. Okay. To understand it diagrammatically, you have one container and you have two liquids, liquid 1, liquid 2. These are mixed. Okay. I am showing these separate, but these are mixed. So there will be some vapor pressure here, P1 and P2, due to both because these are volatile. This pressure will be proportional to the mole fraction of gas 1 in the solution, and this pressure will be proportional to mole fraction of gas 2 in the solution. Okay. Otherwise, it is similar. That's why Raoult's law and Henry's law. Henry's law is also called a special case of Raoult's law. We will be talking about it. Now we can make use of these two. Before we can make use of these two relations and how we can make use of this one, we need to understand Dalton's law of partial pressure. Dalton said that the total pressure over the solution phase in the container will be the sum of partial pressures of the components of the solution and is given by P total equals to P1 plus P2. Total pressure will be sum of all partial pressures. A simple thing he said, which is known as Dalton's law. Varsha, just let me complete it first, okay? So what Dalton said that partial pressures, when we add all partial pressures, then that will result in the total pressure. And what you have seen that if we have, say, water and alcohol mixed together, so water will get vaporized, alcohol will get vaporized, and water produces pressure P1 and alcohol produces pressure P2. So it means total pressure will be P1 plus P2. That's what Dalton said. So in simple terms, what this law is, simple terms, don't think it is something complex chemistry, nothing complex here. So it says that it is a mixture of two liquids. P1 is pressure due to vapors of L1 and P2 is pressure due to vapors of L2. That is what this law is talking about. Now here total pressure will be P1 plus P2. That's what Dalton said. So when we add these pressures due to both volatile liquids, volatile means they can vaporize. Due to vapors of these liquids, pressure created, sum of these pressures will be total pressure. But Raoult said that P1 can be given by P1 not X1. Means if in this container you have only L1, then whatever pressure is created, that will be P1 naught. If you have only L2, then whatever vapor pressure is created, that is P2 naught. Okay. So Raoult interrelated these pressures, P1 with P1 naught and P2 with P2 naught with mole fraction. So here if L1 has X1 moles of the vapor phase and L2 has X2 moles of its vapor phase dissolved into it. Okay, so what I'm saying, it is volatile, but there will be some vapors inside it. The mole fraction of that is X1 inside the liquid, X1 of liquid 1. The mole fraction of the vapors of liquid 2 inside the solution, X2. So Raoult gave a relationship between the pressure exerted by one component in the mixture with its partial pressure when that liquid is present. Only that liquid is present, by using the mole fraction of that particular vapor in the liquid. So first understand what is P1, what is P1 naught, what is X1. If that is clear, then you will be able to understand this relationship. P1 is the partial pressure of a particular component when it is in mixture form. P1 naught is its partial pressure when only this component is present. X1 is mole fraction of this vapor in the liquid when it is in mixture form. So these two are in mixture. This is when pure liquid. Other component is not present. Now, if there is any confusion, let me know. That is what Raoult said. Okay. And this is the relationship you have to remember. Varsha, now is this clear? Or if it is not clear, you need to let me know which part is not clear. So Dalton said that these two partial pressures will give me the total pressure. So P total will be P1 plus P2. So I can write P total equals to P1. P1 is P1 naught X1. P2 is P2 naught X2. And I know that sum of all mole fractions will always be 1. Why? Because it's a fraction. And sum of all fractions is always 1. For example, if 1 by 4, the other component will be 3 by 4. I'll get always 1. Sum of all percentages 100. Sum of all fractions 1. So from here, I'll get x1 equals to 1 minus x2. And I'll substitute in this place x1. I'll write 1 minus x2. P1 naught as it is, x2, P2 naught as it is. So from here, I'll get this relationship. When I simplify this one, I'll get P total equals to P1 naught plus P2 naught minus P1 naught x2. You can use this formula as it is. In numericals, you can use this formula as it is. Okay. So Dalton said, you don't need to explain this one. I'm just explaining because, Otherwise, you won't be able to understand. You may remain confused. But for you, this one is important. This thing is important. Okay. In 12th grade, you won't be asked to derive this formula. You will be just asked to apply this formula. Similarly, here, you will be asked to apply this formula. And when we do numericals, it will be clear that it is just application of the formula directly. Now, graphically, this is nothing but what I have shown as that Dalton said that the sum of partial pressures will be P total, first of all, that point. So in this diagram, there are 2 points I am talking about. First of all, that P total will be sum of P1 and P2 at any point of time. Okay. So suppose at this point I am talking about, so this P total will be sum of P2. P2 is this much here, and P1. P1 is this much. When I add these two values, say this is X, this is Y, the total value I'll get as X plus Y. So that's how I got the line P total equals to P1 plus P2. Now P1, P2, P total all are straight lines. The reason is they are mathematically equations of a straight line. So P1 equals to P1 not X1 is linear equation passing through origin, a straight line passing through origin. P2 equals to P2 not X2, again a straight line passing through origin because they are of the order of y equals to mx, not y equals to mx plus c. It means they are passing through origin because c is 0, y intercept is 0. And this one is also a straight line. This is y equals to c plus mx. Y equals to mx plus c actually. This part is c and this part is m slope. This is x. Okay. So in terms of x2, it will be p total p1 naught plus p2 naught minus p1 naught. Or otherwise, if you substitute this x2 as 1 minus x1, then p total will be p2 naught plus p1 naught minus p2 naught x1 also. Okay. It is just whether you are replacing x1 with 1 minus x2 or you replace x2 with 1 minus x1. So if you replace x2, the equation will be in terms of x1. But again, it will be straight line because it is of the form of y equals to mx plus c. All are straight lines. So here, two graphs are merged. Two graphs are merged actually. And you need to understand this is slightly typically different. So if you are considering only one component, x1, so its mole fraction is 1, it means other small fraction will be 0 because the sum of all fractions is 1. Then in that case it will be p1 naught, and that's what I told you, that if only pure one component is present, if component 1 is present, its mole fraction will be 1. And the partial pressure created by this will be P1 naught. At the other end, it shows only component 2 is present. Component 1 mole fraction is 0. It means it is 100% component 2. And when only component 2 is there, partial pressure created by is P2 naught. That's what we have discussed here. P1 naught is vapor pressure of pure component 1 when only 1 is present. P2 naught vapor pressure of pure component 2. So that's what in this graph we have shown on both ends. Otherwise, here it's a mixture. When we move from here to here in this direction, component X is decreasing, component 1 is decreasing, component 2 is increasing. Okay. If we are moving in this direction, component 2 is decreasing, it was 1, and component 1 is increasing. Now understand. Okay. And that is something I have already told you, that at any point it is sum of the partial pressures. So if I consider here this equation, okay, and this equation, and now consider this equation. When x2 is 0, when x2 is 0, it will give you partial pressure P1 naught. X2 is 0, P total will be P1 naught, because there is no P2. And if you consider here, only component 2 is present, means x1 is 0. When x1 is 0, x2 is equal to 1. And when x2 is 1, it will be equal to P1 naught plus P2 naught minus P1 naught. P1 naught got cancelled, P2 naught. So it means this graph represents the combined reaction, combined equation basically. So what is meant here? It means this line is for P2 equals to P2 naught x2. This line is for P1 equals to P1 naught x1. And this line is for P total. Okay. P total P1 naught plus P2 naught minus P1 naught x2. So you just need to understand that these three lines are actually the graphs of P1, P2, and P total. If question appears from here, you just need to substitute the values of mole fraction in this equation. So even if this graph is given, you need to understand the answer will be calculated by this equation only. This equation actually represents this graph. Okay. So in few questions, you will be given the graphs and you will be asked the questions. In few cases, only one equation will be there. You will apply this formula or this formula. If both equations are given, then you will apply this formula. P2 equals to P1 plus P2 naught minus P1 x2. Okay. You won't try to find the answer from graph. You need to understand it is actually your examiner is asking about the formula you need to use is this one. And you will understand when we do the question. Now, the composition of vapor phase in equilibrium with the solution is determined by the partial pressure of the components. And what is the difference? I'll tell you. Okay. If Y1 and Y2 are the mole fractions of the components 1 and 2 in vapor phase, understand the difference from the previous one. In previous case, I told you that if this is the mixture and you have liquid L1, liquid L2, X1 and X2 are the mole fractions in the liquid. Now we are talking about Y1 and Y2. Y1 and Y2 are the mole fractions in vapor phase. So Raoult gave us another way in terms of mole fraction in vapor phase also. So in vapor phase, if mole fraction of vapor 1 is Y1 and vapor 2 Y2, then he said that it will be given by partial pressure of 1 will be Y1 P total and P2 equals to Y2 P total. This P total will be given to you, yeah, in many cases, or you will have to calculate with the given data. So in general, Pi equals to Yi P total. Understand the difference that Y is mole fraction in vapor phase, X is mole fraction in liquid phase. That is the only difference. Okay? Otherwise, it is similar to Pi equals to P1 naught or Pi naught X. Okay? So the difference here is that here we will be talking about P total. So in both cases, it is P total, total pressure by the vapors. Pressure will be due to vapors only, not due to liquid. So P total will be pressure due to vapors, both vapors. And P1, P2 will be the partial pressures of each component. Y1 and Y2 are the mole fractions of these vapors in vapor phase, not in liquid. In previous case, here the difference was that this mole fraction was mole of vapor in the liquid, mole of second vapor in the liquid. This is the pressure when only liquid 1 is there in the container. This is the pressure when only liquid 2 is in the container. P1 and P2 in both cases are same. These are same. These are same. Partial pressure of vapor 1, partial pressure of vapor 2 in both cases. But depending on whether we are considering the mole fraction in the liquid or mole fraction in the vapor phase, the formula is different. This uh, where is P in? Where is P in written? PI. PI, okay. It is generic form. Basically, I can be 1, 2, 3. So if you have 3, 4 components, so P1 will be equal to Y1 P total, P2 will be equal to Y2 P total, P3 will be Y3 P total. I can be 1, 2, 3, whatever you want. How many components are there? So that is the in general formula. In general, Pi equals to Yi P total. So first thing is you need to memorize the formulas. All formulas should be very clear. Even if the underlying derivation is not clear, that can work because derivation will not be asked. But you must remember how to apply this formula. You must know it. For that, now there is a question so that you can understand. Vapor pressure of chloroform and dichloromethane at particular temperature are 200 millimeter Hg and 415 millimeter of Hg respectively. Calculate the vapor pressure of the solution prepared by mixing 25.5 gram of chloroform and 40 grams of dichloromethane at the same temperature. Second, calculate mole fraction of each component in vapor phase. Remember, there are two components. The components are chloroform and dichloromethane. Chloroform and dichloromethane. Vapor pressure of chloroform 200, vapor pressure of dichloromethane 415 millimeters. So it means it is given these are volatile liquid and they have created their vapor pressures. Okay. So separately their vapor pressures are given. You need to calculate the vapor pressure of solution prepared by mixing few moles of chloroform and few moles of dichloromethane. You actually need moles. That's why I'm calling these masses as moles. So first understand the question, read the question carefully so that when I explain, you get the answer. Varsha Raoult's law can be for more than two, but in your syllabus, it will be asked for two. Because if we combine that, if we talk about the combined formula, that combined formula is only for two. Otherwise, you can anyway calculate the answer, okay, even if there are three liquids, four liquids, by underlying concepts. Yes, Shashwat, correct. Yes, Hashi, correct. Okay, so approach is correct. Yes, you can just tell me the approach, and your approaches are correct. Good. So how do we solve it? Vapor pressure of the solution will be P total, and that will be given by P1 naught plus P2 naught minus P1 naught. Okay. So we say that CHCl3 chloroform is liquid 1 and dichloromethane is liquid 2. P1 naught is given 200 millimeter of Hg, P2 naught is given 415 millimeter of Hg. Vapor pressure of chloroform is 200 millimeter, dichloromethane is 450. We have to obtain a solution, this solution. So for that, we will calculate the number of moles. Approach will be, we need to have P total. For P total, we will need mole fraction of second component. Okay. And to get mole fraction, we need moles of both components, and moles we will get from masses. So this will be the approach. Masses will give us moles, moles will give us the mole fraction of second component, and from there we will get P total. So moles of chloroform given mass upon molar mass, moles of dichloromethane again molar mass, sorry, given mass upon molar mass, mole fraction of x2. Remember, we will calculate only x2, not x1, because in that formula we need x2. So that will be number of moles of second component divided by total number of moles. So we got mole fraction of second component. We substitute all values. P1 not, P2 not already given. Substitute all values. P1 not given 200 millimeters of Hg, P2 not 415 millimeters of Hg. This is we have calculated x2. We get value of P total 347.9 millimeter of Hg. Because the values of pressures are given in millimeters of mercury, we will get the answer in millimeters of mercury, unless it is asked in some other units. For that, if you are asked to get in some other units, 760 millimeters of Hg is equal to 1 atm. Yeah. 1 atm is equal to 0.987 bar if you have to calculate. Okay. Or 1 atm equals to 1.01 into 10 to the power 5 Pascal. These conversion units you should know. Yes, Vanna, your observation was correct. Shimangi, yes. She has correct formula. So I'm going back to the question again. In question, vapor pressures are given of chloroform and dichloromethane. So let chloroform be 1. So in that case, it will be P1 naught. This will be P2 naught. Okay, we need to calculate vapor pressure of solution, means we need to calculate P total, which is P1 naught plus P2 naught minus P1 naught x2. And we need to calculate x2, otherwise everything is given. And for x2 is N2 divided by N1 plus N2. And this information we get from masses, given mass upon molar mass. So given mass upon molar mass will give us the number of moles. From number of moles, we will calculate mole fraction. Mole fraction we will substitute along with the partial pressures, vapor pressures of chloroform and dichloromethane. Shivangi, here I'm coming to second point. Okay. Now, second point, mole fractions of each component in vapor phase. Yes, Shivangi, you are right in that sense, Y1 and Y2. Okay. So because it is talking about mole fractions, we need to calculate in vapor phase Y1 and Y2. What is the relationship? The relationship is in mole fraction in vapor phase. For that, Pi equals to Xi P total, Yi P total. So we will apply this one. How we will apply this one? So let the mole fraction be Y1 and Y2. Approach will be, we need to get Y1 and Y2. We know P1 naught. From there, we will calculate P1. And from P1, we will calculate Y1. We know Y P2 naught. From P2 naught, we will calculate P2. From P2, we will calculate Y2 because P total is anyway known to us. Okay. So P1 equals to P1 naught X1. And X1, we have calculated X2, if you remember. So X1 will be 1 minus X2. So P1 equals to P1 naught X1. P1 naught is given 200. X1 will be 1 minus X2. So we got the value 62.4 mm of Hg P1. The moment we have P1, we know P1 equals to Y1 P total. P2 will be P2 naught into X2. X2 we have calculated. P2 is given, P2 naught is given. We got P2 also. Now apply. P1 equals to Y1 P total and P2 equals to Y2 P total. P total we have already calculated 347.9. So Y1 mole fraction of chloroform in vapor phase, Y2 mole fraction of dichloromethane in vapor phase. These are the answers. Ashwat, Ashi, correct. Shivangi, yes, correct. If any step is not clear, let me know. And the best way is you go to the question and try to find out whether you will be able to recall without looking onto the solution. So I'm giving you few seconds. Both parts, try to understand whether you will be able to recall all the steps or not. And in examination, if you face any problem, write all the formulas related to that particular concept in rough paper, and then try to find out the relationship. What is missing? What is the interlinking? So for example, here in this case, interlinking was P1 and P2. Okay, P1 and P2 gave you the interlinking. So in short, in second case, what you used Y1 P total equals to P1 naught X1. Both are P1. P1 in terms of mole fraction in vapor phase, P1 in terms of mole fraction in solution. Both are P1. Okay. From there you got Y1. Similarly, P2 equals to P2, Y2 P total equals to P2 naught X2. This part I am talking about second part. Okay. So understand P1 is same in both cases. P2 is same in both cases. What is P1? The partial vapor pressure due to component 1. What is P2? Partial vapor pressure due to component 2. What is P1 naught? If only component 1 is there in the container, same container, then the vapor pressure P1 naught. If only component 2 is there, then the vapor pressure P2 naught. What is X1? X1 is what is the mole fraction of component 1 in the liquid. What is X2? Mole fraction of component 2 in the liquid. What is P total? Total vapor pressure above the liquid. What is Y1? The fraction of component 1 in the vapor. What is Y2? Mole fraction of the component 2 in the vapor. Raoult's law, as I said, is a special case of Henry's law, or you can say Henry's law is a special case of Raoult's law. Raoult's law is Pi equals to Xi P1 naught. And if you compare, if you write the Henry's law, it is similar. It says P equals to KH X. It means these two are same if KH is P1 naught or Pi naught. So Raoult's law becomes a special case of Henry's law in which KH becomes equals to P1 naught. And this question appears in 1 mark. This is what you need to write. Write Raoult's law in mathematical form, Henry's law in mathematical form. Don't write the definitions. Exactly what is written here on the screen. Raoult's law, Pi equals to Xi Pi naught. Henry's law, P equals to KHX. So Raoult's law becomes a special case of Henry's law in which KH is equal to Pi naught. So, Pi means for any component, if its Pi naught is equal to KH, then the partial vapor pressure will be same in both cases. Now vapor pressure of solutions of solids in liquids. Vapor pressure of solutions when solids are dissolved in liquids, and these solids are non-volatile. Raoult's law is for volatile liquids. Raoult's law is applicable for a mixture of volatile liquids. Henry's law is different. Henry's law is when some gas is dissolved in the liquid. So gas is different, not the vapor of the liquid. Understand the difference. In Raoult's law, the vapors are of the same liquids of which we have the mixture. Understand the difference in Henry's law and Raoult's law. The difference is here you have only one solvent. Here you have more than one solvent. Solute is a different gas. Here solute is vapor. Rather you say solutes are vapors of same liquids. In other words, you can say partial pressure is due to different gas. Here you say that is partial pressures are due to vapors of the liquids. That is the difference. Although the content inside the liquid will depend on the pressure above it, whether it is pressure created by different gas or due to vapors of same liquid, that doesn't matter. But there is some difference in Henry's law and Raoult's law. Both relate the partial pressure and the mole fraction. Henry's law relates the partial pressure of the gas with the mole fraction of that gas in the liquid only. Okay. Raoult's law, in one case, it relates the partial pressure with the mole fraction in the liquid, and in another case, the partial pressure with mole fraction in the vapor phase, both. Okay. So here it is P1 equals to KH x1 or P equals to KHX. In case of Raoult's law, you have Pi equals to Pi naught Xi and Pi equals to Yi P total. That's what we discussed. Okay. And this one is component wise. If we consider this P total will be P1 naught plus P2 naught minus P1 naught X2. So these are the important formulas you need to remember related to Henry's law and Raoult's law. Next, vapor pressure of solutions of solids in liquids, non-volatile solute. So the vapor pressure of the solution is solely from the solvent. Vapor pressure is because solvent can get vaporized. So suppose I have only water, only water. So all the water molecules which are on the surface, these can get vaporized, okay, depending on the temperature, obviously. How many of these will get vaporized at a time will depend on temperature, but all can get vaporized at a particular temperature. All are eligible to get vaporized. Now, suppose I mix a solute in it, sugar. Say. Now there will be few molecules of solute here. It's not just water. And these solutes are not volatile. So the number of particles now which can get vaporized is less than earlier. Not as many particles or as many molecules can get vaporized now in the solution. Now it is solution. So here it was solvent only. Now it is solute plus solvent. So that's why the vapor pressure of the solution will be different from vapor pressure of the solvent only. This diagram should be clear. So in the solution, the surface has both solute and solvent molecules. Thus, vapor pressure is reduced. Why? Because now fewer number of molecules of solvent can get vaporized. Some spaces have been occupied by non-volatile solute. So the vapor pressure of the solution is less than the vapor pressure of pure solvent. Okay. So in this case, all molecules have tendency to get vaporized, but here fewer number of molecules have tendency. So the vapor pressure is reduced.